And you'll have to come over here in front of the camera.
Organizing this event for us. So I shortly introduce the project CORNET. It's a CORNET project, a 2 years project, and we are now in the middle of the project, and we will present our results. Basically, it's a project where we have 5 partners from Belgium and from Germany. And the focus is on security of IoT, with where we especially look at hardware concepts. So for each of the 5 partners, we have a different focus from technology and also a different type of application. And now it's the moment that Ulrich shows the slide where we have the nice overview of the 5 of us with the different points of attention. So
that's not this one, huh?
Including the one of the view B.
That's not this one.
Okay.
It's
yes, this one.
Yeah,
the number 1, of course.
Yes. So and then we start with Laurent from the VUB that will present us the use case of environmental monitoring and the use of heterogeneous devices. Yes, so you see.
Oops. With a challenging one. No, do it like this. Works. Okay, Laurent, I give the floor then to you in this case.
So,
yeah.
If the slides pop up.
Yes.
Then we can really start.
Present without slides. That's not really the point.
No, that's not the idea. Give me a second, because this is the challenging parts.
The switch.
Okay.
Yes. Okay.
That's a slide deck.
Yes. So we shortly go over the slides with the overview, so that you can see here. It's also the order of the talks, and I said before we start with the talk of the VUB for environmental monitoring on heterogeneous embedded architectures. Please.
Thank you very much. I'm Laurent Segers from the Vrije Universiteit Brussel. And in our research group, we have been working on both embedded security and then both environmental monitoring. What do we understand under environmental monitoring? Well, we all know the weather outside, temperature, humidity, and so on. So the concept is that with a few sensors, we are able to monitor all these things, like in a weather station, to also measure, for instance, vibrations in the city, to see how, if there is a local hotspot of temperature in a city, and so on. We'll also see, well, how green is an area, how well behaving is an area, and so on. So in order to do so, we are developing small embedded systems that on one hand measure all these entities like acoustic pollution, humidity, temperature, light intensity, also the air quality, and so on. And then on the other hand, we want to transmit this data on a remote server so that we can see on the map, for instance, how is the situation evolving over time. Of course, most embedded systems nowadays come with some extra features. But if we talk about small embedded systems, usually we talk about systems with limited memory capabilities, in the sense of 0.5 megabyte maximum, maybe tens of kilobytes of volatile memory. These are not capable of doing a lot of processing either. And we talk about microprocessors of 48 megahertz, 60 megahertz, 120 megahertz. So it's not that we are putting a huge server there which has infinite amount of resources. That means also that we read out sensors at a very low rate, maybe 1 hertz, 10 hertz, and so on. But one of the problems we are facing now is, okay, we can put all these devices out there, but how do we make sure that all these devices send out the data in a safe way? So data integrity and confidentiality is important. Let's say that we are measuring temperature. We don't want to see temperature of, let's say, 2000 degrees Celsius in a city. That's simply impossible. Another problem is how can we trust our own devices? Let's say that one device is being reprogrammed by someone else or being taken by someone else. How do we make sure that we are able to make sure that we can trust this device? One possibility is to use GPS or RTC to check, is the location of the sensor still the same? Is the time of the sensor still the same? And so on. Now, over time, when we have our embedded system put out, typically it's a small device that we put on the top of the building, somewhere in the city. We don't always have the time to go to the sensor physically and to reprogram it physically. So one of the options we also envisage is how to do some secure remote updates. And for that also, we need secure attestation, but also how to remanage in a safe way safe data communication with new keys. So looking at this, we made a list of sensible risks and mitigation solutions. So one of the possibilities is that once we put out the device, we know its location, and usually this device should not move. So we keep track of the device. If the device GPS says, you know, I'm at another location, then the device might be compromised. The wireless communication, of course, we cannot send all the data in plain text, because otherwise other people can read your data, which might contain sensitive data. Let's say if you have an acoustic recording of somewhere, you don't want to be able to read, this person has been speaking about blah, 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 blah. So we need to make sure that our transmission is done in a safe way. So for that, encryption and data integrity is very important. Also, we don't want to have our data being transformed into something else. Again, the example of the temperature at 20 degrees Celsius, it's not desired to have a temperature of 2000 degrees Celsius. So for that, also safe data integrity and encryption is necessary. Other parts are also firmware updates, and then making sure that if we do updates, the updates are done in a safe way. So the embedded systems need to have a minimum set of requirements, preferably embedded in the silicon itself. In the last years, there have been new microcontrollers which implements a lot of new embedded features. One of them is the trust zone, so trusted execution environment. So that allows us to split up the code in two parts. One is a safe code, and the other one is the non-safe code or the non-trusted part. Root of trust for some applications might be interesting. Secure boot and secure bootloaders are also very important. And then, if possible, some microcontrollers come with them, the secure peripherals. So you can say this peripheral, we can assume it is safe, and this one might be compromised over time. And then also optimizations for secure storage and over-the-air support for secure updates over the air. We have made a list of lots of possibilities, but in our group, we have limited ourselves to a few microcontrollers which implement all these features. These have been recently coming out on the market, let's say in the last 2-3 years. They all implement the trust zone environment. They all have power efficient computations, of course, also with very limited processing capabilities and memory possibilities. Some have crypto modules integrated, which allows us to, for instance, implement encryption, hashing, and the like. And some of them exist with trust zone, but also without trust zone. That allows us to have a check on what is actually the overhead of using TrustZone in this kind of devices versus not having this TrustZone thing. They all come at a reasonable price, and we went for the microchip variant, as in the lab we have already experience with microchip. And we have developed our own custom board for this. So this is a small board with lots of I/O capabilities. It's running at 48 megahertz, but we have a crystal at 32 megahertz. And the nice thing about it is, with the microchip version, this chip can be interchanged. So we can keep the same board. Everything still keeps the same, except that you can interchange this chip with the TrustZone variant and the one without the TrustZone implementation. So that allows us to do a fair comparison between the two platforms. This chip offers a lot of capabilities already implemented in the silicon itself. I'm going briefly over it. So it's an ARM33 based platform. It's a light brother of the ARM33 platform. It offers a TrustZone, and you can then select until you can then say, okay, now this code belongs to this place, and this code belongs to the non-secure part. It offers true random number generator, lots of crypto hashing methods, also public key validation support, +1 internal key storage capability, secure attestation, and it has optimizations for secure storage, and then also trusted IOs. So you can then select this sensor goes to a trusted part, or this sensor goes to a non-trusted part. To do so, the microcontroller has effectively implemented separate registers. So for instance, if you want to have a UART in the trusted zone, then you're using a separate set of registers compared to the same UART, but then in a non-trusted environment. To measure some sensors, we have also implemented our own sensor board, which is fully compatible with the previous board I've shown you. We have limited ourselves to a GPS module, light sensor, humidity temperature sensor, accelerometer, and a microphone. It also has place for SD card storage for local logging in case the wireless communication fails without reason. Now, having the microcontroller itself, it's very nice. Everything is already embedded in the silicon, but that also means that in the software layer, you need to do some thinking before you implement your application. So that means on a normal microcontroller without a TrustZone, one would usually do all the drivers for the sensors, which interact with the physical layer of the board itself. And then all the data is gathered here in this realizer, plus communication, then is sent to a local or remote server. However, when you're dealing with microcontrollers with TrustZone, you have to think what I'm going to put in a TrustZone layer and what am I going to put in a non-trusted area. So this is usually the application and software engineer would write on a normal, regular microcontroller. And this is the part that is new in the microcontrollers. And then you have to think, one of the things is, but why don't we put everything in the TrustZone area? Well, that would again say, okay, we put everything in there, but that would defeat the security feature of TrustZone. So for that, in a TrustZone, you keep only the parts that you really want to be secure, that are not going to change over time. And here you have your application that does the usual stuff, communicating with the remote server and so on. Between these two, it's very important. The communication usually, this part cannot usually communicate with this part. So except via special function calls. For those interested, I can explain later. But this part can always look at this part. So there is a special execution here that says this part can access this part completely, but not the opposite way. So that's very important when you think your application. The considerations that we have to do is, without Trusted, we only have one application flow, one main loop, you read out the sensors, and you communicate. With Trusted, we have two program flows. That also means two program spaces, two memory spaces, two different sets of registers. These are physically implemented in the silicon. So you have to rethink your application to handle correctly trust zone and the non-secure zone. There are several, you can implement some function calls between the two zones, but you have to really think about, do I really need these function calls? The less function calls you have, the better it is, because these are not, these do not come for free. I'll explain later. Also, not everything can be implemented in trust zone. I explained already, you can implement the peripherals in trust zone. You can implement some code in trust zone, but not everything, especially libraries, do not support all the time trust zone. Why is that? Because sometimes you get pre-compiled libraries, and these are already compiled to be able to handle the non-trusted part. But in the trusted part, you have special assembly instructions, which are not provided in the libraries. And then when you try to compile it, you will get an exception like, sorry, this library is not compatible with this part. That's really a thing that you need to keep in mind. Also, last but not least, when you have peripherals in the trusted area, you cannot use them in the untrusted area, and vice versa, except via special calls. So how did I do it in code-wise? So instead of having each sensor with their own functions and so on, I've subdivided everything into a serial communication. So you have here the serializer and communication communicates with the remote server. Here you have your data stream. This data stream is then split up for each of the drivers. Each of the drivers knows, okay, this data stream, I need to parse it in this way. It's always the same function methods. And then also going here, everything is encrypted and using a hashing mechanism to make sure that the data is safe, transmitted in a safe way. It's a bit the same as in the OSI model. Every piece of software takes off one layer of the data before it gets to the drivers and vice versa. Now, what's the overhead? What's the cost of using these functions, these functionalities? As long as you don't use trust zone, there is virtually no overhead. That's normal because then you don't communicate between trust zone and non-trust zone part. But if you want to go from a non-secure part to the secure part, you typically have like hundreds up to 1,000 cycles of overhead in execution time. That's not a lot. Compared to an application where we have like almost 200 kilobytes of data code, a few thousands of cycles is not that much. So typically 1, 2, 3, 5%. Depends on the application size. If you have a big application, then the overhead is quite small. If you have a small application, the overhead might be quite considerable. Another thing to keep in mind is the microcontrollers we use have 500 kilobytes of code memory. Now you have to divide it in one piece for the trusted area and another piece for the untrusted area. This means that you lose data space, code space for your application because you need to allocate space for one or the other. The minimum set code for the trusted area is about 15 kilobytes, but you need to provision. In a tool, in advance, you have a slider, and then you have to select this amount of memory goes there, this amount of memory goes there. So that's also a thing to keep in mind. We have for now put it at 20% provisioning for the trust zone and 80% for the normal application. And then the secure transmission, that's also very important. We are dealing with small microcontrollers with a few data to be sent, typically 50 bytes, 60 bytes, 80 bytes. Then we get all the sensors read out. If we apply hashing and encryption on it, we almost double the amount of data transmitted in one packet. That's also something to keep in mind. Sometimes it's better to keep lots of data locally and then only transmit when you have enough data. That's a slide that originally I didn't want to put here, but I'm still going to put it here. The using TrustZone and especially TrustZone with microchip might be challenging. Colleagues at my workplace usually hear me, oh, no, it fails again. Because Harmony is a really nice tool. You can say, okay, I want this peripheral, I want this peripheral. These are just being graphically presented as building blocks. You can select, you can drag and drop them on your worksheet. All very nice. It works very nicely in the beginning. And then you say, generate libraries, it does it. But then once you come back later, you want to add a sensor, it sometimes gets really tricky. And it gets really tricky once you want to transfer a sensor from the trusted area to the non-trusted area and opposite. So my suggestion is, first think about what do you want to place where, what do you want to use, and how do you want to use it, and then generate it only once, and then continue with your base code to design your application. But typically, I would not recommend to go back to the design phase. You have to do it in advance. So to summarize, we have selected an ARM23 platform on which we develop some code and we are capable of reading out sensors. We are able to use TrustZone and also to do remote communication in a safe way. We also have seen that designing firmware for this kind of platforms is not always trivial. So therefore, there are some challenges that you have to take into account, preferably from the beginning, not when your thing is already ready, because then you have to redo everything anyway. So do it from the beginning. However, we still need to do a fine-grained analysis on the impact of these silicon implementations, especially TrustZone. And then we also need to do some remote programming of application, secure attestation, and also exchanging in a safe way new keys in case of later data transmission. I've also discussed the problems you might encounter with these tools. I'm not saying these tools are bad. By the contrary, they help you a lot, but you have to take these considerations into account. Voilà. And then I conclude. I would like to thank you.
Thank you. Great.
If there are questions.
So if it would need to be implemented in an industrial setting, how far would you see that it still needs to be further?
So you can use this chip, well, in industrial setting anyways, you have the security problem. I would not use it directly in nuclear power plant, for instance, but let's say you want to drive some robotic arms in on a conveyor belt and the like. And then especially you need their security.
Mm-hmm.
Then I would choose some sensors that you really trust, that you know, okay, these sensors, they cannot be hacked. And then if you say, okay, this sensor do strange behaviors, then you would stop the microcontroller itself. It's better sometimes to say we stop the microcontroller than to do things we don't want to do. If I go back to what I've seen now, yes, the Harmony platform is really nice. That's only the first layer of development phase. Mm-hmm. Because you have the CMSIS library coming from ARM itself. That's a stable platform. And then I would develop on top of the CMSIS one. So the Harmony is a first place to see, okay, how is the code being implemented? But then if you really want to do some secure things in the industrial environment, I would develop my own drivers on top of it instead of going with the Harmony any further.
Okay.
It costs a bit more, but in the end, it's a more stable way of using the microcontroller. And I think that's also a thing that that's also something that some companies do. I've seen this with companies for wind energy. They develop their code, and then they see, okay, these are the functionalities, and then I detach myself from the GUI, and voila. I don't know if that answers clearly the.
Yeah, so, yeah. I mean, I think it's still a pretty steep learning curve.
It's the trust, especially the trust zone, is very steep, because it's not always that easy to tell. Okay, I need so much memory space in this one, and I need so much memory space in this one, and then in the end you end up with, oh, I need double the amount of memory in a trusted area while I don't have enough memory. Also, a thing that I faced is in the normal microcontroller, so without trust zone, I'm using already 50% of the chip. Not because my code is that large. I think the code is about 2,000 lines of code, so that's not an enormous amount, but you need all these libraries. For instance, the crypto one is already like 70 kilobytes. And then you have all these peripherals. That's also a lot of memory that you lose. So these are hidden things. You don't expect it at first, but then if you want to split up in trust zone and non-trust zone, sometimes it can be a challenge. So yeah.
Is the memory the main constraint that you have?
At this moment, yes. Because at the first point, I thought, oh, 0.5 megabyte of memory, plenty of space. But I'm not doing lots of crazy things with this microcontroller. Just reading out humidity, temperature, GPS, light, and some other sensors, basic stuff. And then, even then, I end up already with 50% of the memory being used up. Yeah, of course, I also have the crypto engine behind it. So it's not fair to say it's only the sensors, but you also have the crypto engine, you also have your data allocation and so on. But yes, it can be tricky. Yes. Yes.
Library, so is it only software, or do you have?
You can choose. You can choose. So the microchip gives you the Wolfcrypt library. It's a well-known encryption library for ARM platforms. And then in the Harmony thing, you can select, I want it in pure software, or I want to use the crypto engine. But I've tested it and I don't see a difference.
The size of the code.
No, it doesn't. So I wonder why, because I would say, okay, you then just have a. But as I said, yeah, the Harmony platform is not that perfect. It's a very nice tool. You also need to be warned about, okay, what is it actually doing?
Yeah.
Very quickly.
Yeah.
Any quick answer?
How do you trust the sensor?
That's a good question.
Okay, so that's not an easy answer.
That's a good question.
But some people are doing copy then.
Yeah,
It's a very good question.
Thank you, Laurent.